You tap a thumbnail on your screen and the video starts playing. It feels instant, effortless, and entirely predictable. The interface is so smooth, it tricks our brains into relying on an outdated mental model. We instinctively think that uploading or watching a video is just like moving a file from a folder on our phone to a folder on a server somewhere. This animation shows how quickly that mental model breaks down at scale. A single video file is insignificant compared to the 500 hours of video uploaded to the platform every single minute. And that incoming mountain of data is dwarfed entirely by the 5 billion views requested by users every single day. If platforms operated like traditional file hosting, streaming a 10 gigabyte video would mean waiting 15 minutes for the entire file to download before hitting play. Worse, if your cell signal blinked for even a second, the network connection would drop and the entire download would have to start over from the beginning. Handling this volume of traffic requires the architecture to move beyond simple storage. It fragments every upload, reconstructs into dozens of versions, and scatters across a global network. This fragmentation starts the moment you click upload. Your device takes the original video file and chops it into tiny chunks, usually around 5 to 10 megabytes each. The app then requests a pre-signed URL, essentially a temporary security pass, and starts firing these individual chunks directly into a cloud storage blob. Breaking the video down on your actual device enables resumable uploads. By sending discrete chunks, the system tracks exactly which pieces have successfully arrived. If your Wi-Fi cuts out halfway through, you don't lose the whole file. The system waits and eventually resumes the upload from the exact chunk that failed. Keep in mind, millions of people are firing chunks of data at the servers at the exact same time. The backend architecture would instantly buckle if this traffic wasn't perfectly balanced as it came through the door. This diagram maps how inbound traffic is managed. You can see the pathway moving from the client laptop, routing through the internet, and distributing into the maglev load balancing layer. This spreads incoming chunks evenly across backend machines before reaching final service endpoints. Slicing the file into pieces ensures this massive intake succeeds, regardless of how slow or unstable the user's connection happens to be. Once all the chunks arrive and are stitched back together in storage, a specialized task scheduler called a directed acyclic graph takes the reconstructed video and slices it up all over again. But this time, it cuts the video into independently playable time segments. This animation shows a single video timeline dividing into discrete, playable chunks, usually 5 to 10 seconds long. A 1-hour upload suddenly becomes hundreds of independent micro-video processing tasks. Each of these short segments must be transcoded from its original RAW format into highly compressed formats like VP9, which drastically reduce file sizes while maintaining visual quality. Doing this on standard server CPUs is incredibly slow. Handling a platform's daily upload volume would require roughly 10 million standard processors running nonstop. Standard chips couldn't keep up, so Google engineered their own silicon, the Argos Video Coding Unit, or VPU. These custom chips are built to do one highly specific mathematical task as fast as physically possible. A single VPU grabs a 5-second segment and simultaneously churns out dozens of different versions of it, encoding it into 1080p, 720p, and 480p, and multiple different codecs, all in parallel. Designing custom silicon is an extreme measure, but mathematically, it's the only viable option. Without it, the sheer cost of the server space and electricity required to compress this much video would bankrupt the operation. We now have a fully processed video, but we can't stream it to viewers from a central data center. Dragging heavy video files across oceans and continents for every single view creates massive physical latency. Instead, the system generates a manifest file. Think of this as a detailed index that maps out the exact URLs for every single resolution of every single 5-second segment we just created. The platform takes those highly compressed segments, along with the manifest file, and pushes them out to a content delivery network, specifically Google Global Cache nodes. This map illustrates how the data leaves the central hub. Instead of sitting in a remote server farm, the segments are distributed to physical server racks installed directly inside your local neighborhood internet service provider's facilities. By positioning these edge nodes right next to local network infrastructure, the video you want to watch physically lives just a few miles down the street from your house, effectively neutralizing the latency problem. All of that complex ingestion, transcoding, and caching happens before you even open the app. Let's return to the exact millisecond your thumb taps play. Your phone immediately downloads the manifest file and uses it to locate the nearest cache node. Then it pulls down just the first 5-second segment of the video from that physical rack sitting down the street. It knows exactly which version of the segment to grab thanks to adaptive bitrate streaming. Your device constantly monitors your current network bandwidth, selecting the highest quality file size it can comfortably download in that exact moment. This chart demonstrates the real-time swapping mechanism. If you walk into a dead zone and your cellular connection drops, your phone doesn't pause to load. It consults the manifest file and seamlessly requests the next 5-second segment in 480p instead of 1080p. As your signal strengthens, it steps back up to high definition. Because the segments are so short, your phone is continuously negotiating the best possible quality every few seconds. The system fragments the file, processes pieces of custom silicon, and disperses them to neighborhood racks. All of this occurs in the milliseconds before playback, making the underlying complexity of the network entirely invisible to the person watching the screen.